Yes, sir. Recording is started.
Yes, sir. Recording is started.
Okay, great. So let me share my screen first. Okay, is my screen visible?
Yes, sir.
Yes.
Okay, great. So this is our last chapter um, of our course. So this is called control system theory. So no, okay. Sorry for the interruption. So what I was saying that we have the last chapter to cover, and in this chapter we will have some mathematical terminologies, some mathematical term, and as well as we will have some theoretical part also. Okay, so it generally takes three classes to complete, but I will try to complete it within two classes. So in the next class, I will try to wrap whole things up, and that class might take a little bit more time, but I will try to finish it. Okay, so let's start this class. So what is control theory? So in our first chapter, we knew that in a robotic system we have three individual component, right? So the first component is sense component, second one is control, and third one is actuation. So by consisting of these three components we can construct a robotic system, but out of these three components the main component is the control component, because this is the brain of a robotic system. So, in order to control a robot properly, we need some solid algorithm, okay? Some solid theories, which can be applied to a controller, and that can help you to control your robot properly. So, in this chapter, we will try to understand what is the control theory and how can we use this control theory in our controller so that the controller can work properly. Okay, so uh, in summary, control theory is a specific phenomena of a robotic system which works on a specific basis, and that basics is you have a desired things to achieve. Let's say you have a controller and you set a desired goal which the controller needs to achieve by using the robot, and you are evaluating that if your robot is accurately achieving this goal or not. Okay, so that is the basics of a control algorithm, and you will have to design a controller which can accurately achieve your goal which you have set for the robot. Let's say you have set a goal for the robot is to pick up an object from a specific position, and if your robot is successfully completed this task, then you can say that your controller is working perfectly. But if your robot is failed to like pick any object from a specific position, then you need to rebuild your controller again, right? So that is the basics of a control algorithm. So when you hear the word control, you should remember two things. The first thing is the desired goal, and the second thing is what the robot is actually doing. So that is called the actual output. So there are two things. I'm saying it again. The first thing is desired value, and one is actual value. And you will always try to evaluate what is the difference between two, right? If the desired values and the actual values are the same, then the difference will be zero, and that will make your controller a good controller. Okay, But if the difference is large, that means the controller is not working properly. Okay, so that is the core basics of a control algorithm. So a controller is basically a mathematical analysis. It's obviously a mathematical analysis. You should have some mathematical formula or mathematical definition within your controller that the controller needs to match or needs to follow, and those algorithm will help you uh, to analyze the behavior of a dynamical system. So what does dynamical system means? A dynamical system means that the behavior of your system is not static. It will change time by time. Maybe it will act. That means you can't predict the output of your system. That is called the dynamical system. Okay, and as the name suggests, as you are not being able to predict the output of your dynamical system. That means the controlling the output is very difficult, and those difficult tasks will be achieved by using some mathematical model and algorithms, and that will help you to achieve your desired goal as much as possible, okay, or as close as possible. So that is the underlying basics of a control theory. So let's imagine a case where you have a controller and you have set a value which is 3 radian per second, and you need to you are trying to control the velocity or rotational velocity of a motor, and you set the value as 3 radian per second. Okay, and the controller have taken the input of 3 radian per second, and after taking the input it will try to generate a signal which will rotate the motor at a specific velocity of 3 radian per second. Okay, so that is the ideal point of view, or or this is the ideal case. Okay, so the controller is required to maintain the 3 radian per second, but if the controller fails to reach that goal, then you should say that the controller is failing. Okay, so this is the basics of control system. You will set a predefined value, and you will evaluate that if the output value is deviating from the value that you have set or not. If the output value is not deviating, that means the controller is working fine. So you can represent this same diagram, the same things with a diagram. And in this diagram, you can see that there is an input. This is basically an input, and you can say this input as a required processes response. The two things are the same, and that input is going to the controller, and the controller will recognize this input, and it will convert this input to a specific value, and that response, that value which the controller will generate, is basically a signal, and that signal will go to the process. And what is the process? The process is basically the motor. Okay, the motor process is basically the things that the controller is trying to control. Okay, so in our case, process is the motor. Okay, so can you tell me what is the signal that is required to control the process, or what is the signal that is required to control the motor? What is the signal? What is the type of the signal?
Input signal.
Sir, Boolean.
No, it's not Boolean signal. It's a electrical signal. Okay. So if you want to control a motor, you need to provide some voltage to it. Okay, so a specific voltage will rotate the will create a certain amount of rotation. If you supply a smaller voltage, it will create a less amount of rotation, or the velocity will be less. But if you supply a large amount of voltage, then it will create a huge amount of rotation, or let's say it will create a high amount of velocity on the rotational velocity to the motor, right? So you can control your motor by varying the voltage. Okay, if you vary the voltage, the rotational speed will also vary, will also change. Okay, so the controller will do the same. It will vary the voltage. It will to control the actual velocity of the motor. So if you set some specific velocity, the controller will try to create a corresponding value, voltage which will match with your required value. Okay, let's say you have set 3 radian per second as your required value, and the controller will try to generate a certain amount of voltage that will create exact same amount of rotation that you are required, that you set for your controller. Okay, so let's say the controller is generated 2.5 voltage, and maybe this 2.5 voltage is enough for generating 3 radian per second for the rotation for the motor. Okay, so this is the whole diagram of a control system. But as you can see that in this specific diagram, the process is acting like a motor, and you have set at the velocity as 3 radian per second, and your motor is rotating as 3 radian per second, let's say. But now what you have, but now you have inputted another exception, and that exception is you have inputted a disturbance. Okay, so what is the disturbance? Let's say you are trying to resist the rotation of the motor by putting your hand on the wheel. Okay, so the part that is rotating, the rotational part of the motor, you are trying to resist the rotation of the motor by using your hand. Okay, as you are resisting, that means the rotational speed will decrease, right? So as you are inputting some disturbance, the resist as the resistance to the rotations by your hand, then let's say the rotational speed is decreased to 2.2 radian per second. Okay, so as the output, the velocity is decreased, or the output velocity is changed for a specific disturbance, this will not this will not be considered by the controller. Okay, or what we can say, or we can say that the controller doesn't know about anything uh, about the output. Okay, the controller doesn't know anything about the output. The controller doesn't know what is happening in the output. Okay, because the information that is flowing, it is flowing in a single in a what we can say, it is not it is flowing from one side to another. It is flowing from left side to right side. Okay, there is no backflow. You are not calculating the velocity of output, and you are not providing this velocity to the controller. Okay, as you are not calculating the velocity of the output, and you are not providing the velocity to the controller, again, that's why we are saying that the things that are happening in the output will not be known by the controller. Okay, that is unknown for the controller, and this type of controller is called, sorry, this type of controller is called open loop control. Okay, when you are using a control where you are not giving the information of output to the controller, that is called the open loop control. But now, what we can do, or what we can say, that this type of control is very simple, and it will fail eventually if you have some disturbance in the output. Okay, so how can we solve this? We can solve this by using a simple things. We can integrate a sensor which can measure the output velocity of the motor, and this velocity, after measuring the velocity, that velocity can get inputted to the controller again. And if we can pass that measured velocity to the controller again, then the controller will try to change the velocity so that the disturbance will get mitigated. Okay, So that's the point. So now we are in this case we are using a sensor. That sensor will be used to calculate or to measure the actual angular velocities of the motor. And after measuring the velocities, the controller, it will get passed to the controller. Okay. So you can see in this diagram that the feedback here, the feedback is basically the sensor that is measuring the actual velocity of the motor. And after measuring the velocity, it is passing the measurement to the input again. Okay. But now you can see that this is a block. We can say that all of these things as a block, and all of those block always accept only one input, and it will always generate only one output. Okay. But here you can see that the we are passing an input, and we are calculating the actual velocity by the sensor, and the two signal is getting merged here, right? But we cannot provide two signals to the controller as an input because a block cannot accept more than one input. Okay. That is why we are using an operator here. This operator is called summing point, and the another name of this comparator is called another name of this element is called comparator. And what this comparator is doing, the comparator is basically making the difference of input and the actual velocity or the output. Okay. So this operator is basically subtracting the input, subtracting the output from the input. Okay. So this operator is doing like this. So this value, the difference of input and output, is called error. Okay. So this error will get inputted to the controller, and controller will then try to utilize a way so that the error will get to zero. Is it clear? If the error is zero, what does it mean? If the error is zero, that means input and output are the same. And if the input and output are the same, that means you are doing exactly what you are expected to do, right? So
Yes, sir.
the controller will work such a way that the error will reduce to zero. So it will try to minimize the error as much as it can. Okay. So this specific control is called closed loop control. Why it is a closed loop control? Because you can see a clear loop here, and this layer is closed. Okay. So that is why it is called closed loop control. And this closed loop control is vastly used in different type of controller because it is very feasible and very effective in different type of application. But open loop control is very simple, and it is not being used in like variety of system. It will only be used in some specific type of scenarios where the system is very simple. Okay. But closed loop control will be used in like most of the application. So here you can see that this is basically the closed loop control, and we are representing this closed loop control as a block diagram. Okay. So here you can see that you are inputting a you are passing an input here, and you are using a sensor to measure the output value, and that value is getting inputted to the operator which we already talked about, and that operator will create the error, will calculate the error, will not create the error, sorry, will calculate the error, and that error will get inputted to the controller, and that controller will then try to create an signal, a signal. That signal is basically the voltage signal. Okay. That voltage signal will get passed to the motor, and this part is basically the motor. And now we are dividing this motor part into two segments. One segment is the power amplification, and second segment is the motor itself. So this is the motor actually. But before the motor, we are using another block here. So what this block is doing? This block is called power amplification. So before understanding the power amplification part, we need to understand the controller part very clearly. Okay, so the type of controller that we generally use is our it can be Arduino, or it can be Raspberry Pi or JSON Nano. Okay, those are the controller that we generally use in our to build our robot. Okay, but all of those controller have a limitations. So what is the limitation? The limitation is all of those controller can generate a voltage which is minimum. The minimum range of this voltage is 0, and the maximum voltage of that controller can generate is 5 voltage. Okay, so the voltage range is 0 to 5. So a controller can generate a minimum voltage of 0 and a maximum voltage of 5. But the motor you are using in your robot is not bound to 0 to 5. It can be 12-volt motor, it can be 24-volt motor. If you are using a 12-volt motor, that means that motor is expecting 0 as the minimum voltage and 12 as a maximum voltage. But the voltage, the voltage that is coming from the controller is bound to 0 to 5. But the motor is expecting 0 to 12. So how can we match the expectation of motor with the supply of the controller? So the matching is performed by using the power amplification part. This power amplification will try to match the controller voltage with the motor voltage. Okay, so it will amplify the voltage such a way that the amount of voltage that the controller is generating is getting exactly matched with the motor expectations. Okay, so that is the whole that is the purpose of using the power amplification part. Okay, so power amplification is valid when you are using a motor that is having a larger amount of voltage range than the controller has. Okay, so that is the main purpose of power amplification, and you can omit the disturbance part from here. So this is called the characteristics of a feedback system. Okay, if you are asked in your exam that you need to write the characteristics of a feedback system, then you must need to draw this diagram and explain this diagram with any example is you can imagine. You can explain this diagram with a motor example or anything you can imagine, but you need to explain each and individual part of this diagram. Let's say the controller part, the error part, the power amplification part, the controller part, the motor part, and the sensor part. All of those parts is are needed to be described in your answer. Okay, so that is the characteristics of feedback system. So I have already talked about this component. You can just read it. I have already talked about it. Now I want to talk about a specific part which is called the stability of a system. Stability is very important in any type of controller. You evaluate if your system is stable or not. So how can we calculate a system is stable or not? Let's say you have a controller, okay, and you are using this controller to control a motor, okay, and you set a value of 5 radian per second. That means you are expecting that the motor will rotate it at exactly 5 radian per second, right? That is the goal of your of the controller. Okay. Now, at a certain the controller will not jump to the 5 radian per second like from the beginning. Okay, firstly it will try to increase the voltage, and it will see that what the actual velocity of the motor at that time. Maybe the at first the motor will have like 2 radian per second at first. Okay, so then this value will get measured by the sensor and it will get passed to the input again, and then the controller will try to modify the voltage, and then that will create the increase in the actual value, and that value maybe will increase to 4 radian per second, and then it will get to the 5 radian per second. Okay, so this, to achieve the 5 radian per second, it is a basically a gradual process. It's a sequential process. You can't achieve 5 radian per second from the beginning. Okay, you at least spend some time to like match with the required value which you have set. Okay, so the amount of time that is required to make your system stable. So what I'm trying to say is that when you have achieved this 5 radian per second value, that means you have matched with your required value, right? At this stage, your system is stable. Okay, so when you have matched with your required value, when your actual value is matched with the required value, that state is called stable state. Okay, so when you have achieved the stable state, let's say your motor is rotating exactly at 5 radian per second. Now what you will do, you will input and disturbance. You will input a disturbance to it. Let's say you try to reduce the you try to resist the rotation of the motor by using your hand, which I have discussed you all discussed about it earlier, right? You If you try to grab the wheel of the motor, then the motor will start rotating at a less amount of rotation, right? The rotational speed will get decreased. So that is the disturbance. So when the controller encounters any disturbance, how much time it will take to overcome this disturbance is called the stability of the system. Okay, so the less amount of time the controller requires is will be the more stable controller, and the more amount of time the controller is required to like overcome the disturbance will be called as more less stable system. Okay, so that is the stability part. Now, as I have already told you that the system will not jump to the required value at the first step. Okay, it will take some time to get stable. So let's say you have set your 5 radian per second and your system will start rotating. So at first the rotational speed will zero, and the rotational speed will get increased. And interestingly, the rotation will not get fixed to the 5 radian per second at first. Okay, you will see that the system will climb to a hill. Okay, it will basically it will try to achieve the 5 radian per second, but it can't achieve the exact 5 radian per second at the first run. Okay, maybe it will achieve 5.2. Sorry, maybe uh, it will achieve 5.2 first. Then it will realize that, oh no, I achieved more than I required. Then it will try to reduce the velocity. Okay, and that velocity will get reduced, and then it will get increased. So in this way the ups and down will happen, and eventually after a certain amount of time it will get saturated, and it will get the exact value that is 5. Okay, so when you get the exact amount of value that was required, that state is called steady state. But before achieving the steady state condition, the state which you are in is called the transient state. Okay, so the unstable state, or the state where the signal is not getting stable yet, is called the transient state. And after getting the stable state, you can see, you can say that this state is a steady state. Okay, so that is the concept behind the steady state and the transient state. Okay, so now I'm at the last stage of our class. So as you can see that this is the curve that we have found from the response of our controller. Okay, the controller is responding like this. So if we convert this signal to a mathematical formula, then this can be a very complicated formula. Maybe the T4 to T4, 5T square TTO plus 2T square, right? This type of equation can be it can be required to illustrate this type of signal, right? But as you can see that this type of nonlinear equation is very difficult to analyze. So if you are required to analyze this mathematical equation, you will have to spend a lot of time to calculate different type of things. Let's say if you are required to calculate the root of this equation, then you will need to calculate it with a greater amount of computational power, right? So what I'm trying to say that this signal is defined as time domain signal because we are calculating the response with respect to the time. So 1 second, 2 seconds, 3 seconds. Okay, but as we are representing this signal as time domain, this computation is getting harder. So what we can do, we can convert this time domain signal to frequency domain signal. So when we are converting a time domain signal to a frequency domain signal, the signal will get simple, and you can calculate or you can analyze this signal by using some predefined technique, and those techniques are very simple. Which, if you compare the analysis in the time domain, you can clearly see that calculation of frequency domain is very simple with respect compared to the time domain analysis. Okay, so that is why we will convert this time domain signal to frequency domain signal. So how can we convert a time domain signal to frequency domain signal? We can use different type of transform, or we can use Laplace transform, Z transform, Fourier transform. Okay, so those kind of transform will be effective to convert your time domain signal to a frequency domain signal. Okay, but we will not go in any deeper of a Laplace transform or a Fourier transform. We just have to know that those are the transform that are required to transform a time domain signal to a frequency domain signal. That much information is enough. Okay, so that is all, and in our next class we will try to know about the block diagram. So what is a block diagram? A block diagram is a phenomena which is used to represent your control signal or your control uh, structure by using some block. Okay, by using some blocks, those blocks will be used to accurately represent what the actuator, what the actual system is doing. So as you can see that this is the input and this is the output, and here you have a block. So the block is having some tasks in it. Maybe it has some mathematical formula in it, and those mathematical formula will be performed on the input to calculate, to make the output. Okay, so we, in the next class we will be looking at the at different type of block diagrams, and on that class we will try to know about the process that will be used to solve this type of complicated block diagram, and this block diagram can be reduced to a single block. Okay, This is very interesting. Here you can see that various amount of blocks are present here, right? But all of those blocks can be reduced to a single block. This is simply like uh, in an electrical circuit, you have different type of resistance in it, right? And you can convert all of those resistance to a equivalent resistance, which resistance can work the same thing that all of those uh, resistance combinedly strain, right? So this resistance is called equivalent resistance. So similarly, a single block can be calculated, which can do the same things which the whole diagram is doing. Okay. So in the next class, we will learn how to calculate the single block uh, out of all of those given out of the given diagram. That the diagram is having that diagram is having a lots of blocks in it, and we can reduce all of those blocks to a single block. Okay. In the next class, we will go into deeper. Okay.
Okay, sir. So when will you have a quiz? Quiz 3.
So okay. So I will take your quiz free maybe on Saturday because I have to take another class. I had a initial plan to take your quiz on uh, Thursday, but it is not possible because I have just completed one lecture, and
Sir,
I
I have a
I
one meet final exam. Sorry, final exam of 423 at Sunday.
okay.
So
So
is it possible if you will take the online quiz?
no, it's not possible to take a quiz on online, but rather we can I can set a different time or a different day, uh, which can suit with your exam routine. Maybe we can uh, okay. You can give your quiz on Sunday, maybe. Is it possible?
So Sunday 5:30 from 5:30 is my exam. So after like
Okay.
so it will finish at 7 p.m.
Okay. No, okay. So that is very late. So.
Yeah.
Mm, okay, so can you give so do you have any exam on Saturday?
No, no.
Okay. Um, but I will request you to come for to attend the quiz, and that quiz will last only 20 or 25 minutes. You
Okay, sir.
just
Okay, sir. I'll
okay.
come at 7.
Okay, okay, great.
And the topic will
So
be, sir?
I will announce the topic later because I will take another class tomorrow,
Okay, sir.
and I will also take another class on Friday also. So that will complete our whole syllabus. Okay.
Okay, sir.
So after completing the whole syllabus, I will announce the syllabus for the quiz. Okay.
Okay, sir. And for
Okay.
final syllabus, there will be two chapter, like one from navigation and one is control.
Yeah, yeah. The syllabus for the final exam is the navigation and the control theory. The two
Okay, sir.
chapter. Okay. So that is all for today. Thank you for joining. I know
Thank you,
it's
sir.
very it's late night. So I'm ending the class now.
Okay,
Okay,
sir.
thank you, sir.
Thank you.
Bye.
Good night.
Good night.